just and I wrote here so that it remains to you for telecom. Okay, in telecom there is a training and a payload. So the vector is UT and UD. Everything travels into the channel. This channel is over the bouncing on the wall and everything that is received there. What I receive here is XT and XT. XT is the training part in the packet, and XT is the payload in the packet. Okay, so I receive packet. Okay, dum, 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 dum. Then what I do is the following. I use the training. Training is known as the receiver, so I use the training. I create a convolution matrix and then the pseudo inverse to get G, which means I get a channel. I get an estimate of the channel. Then for the second part, for the payload, the data, which I don't know. So what I do, I just repeat the same process. But since when I'm making the deconvolution, I need to know what is G, and since G is what I estimate in the previous step, so I just take this G and create the convolution matrix for that. Okay, this is a quite well established procedure for telecom to receive, so to manipulate the block type data, which is called block type is a packet. Okay, so and the first need to manipulate the data in this way by using matrices is by the GSM. GSM was the first protocol in wireless where there was the strong need to manipulate the data in packets. Okay, and by the way, I remember at those times that the industry and everybody was not used to manipulate the data in packets, and I remember that they had to think in packets, and they had to think into processing and estimating parameters in packets, making the convolution in packets, okay, which is slightly different. So saying in one word, you need to revisit the processing in block, which is what we do in this course. Okay, so now one more. Sometime we need to make the filtering for periodic signals. Okay, now if the signals are periodic, which might happen. Okay, so what is a periodic signal? As you quite know quite well, but so a periodic signal is an aperiodic and then is repeated periodically. Okay, so a periodic signal is I take this signal and then I repeat. So I take these, let's say, let me use that word. Okay, so we call this one as x tilde. Okay, so this x, okay, which is a block of data, in order to make it periodically, what I need to do is that I conform with a set of data. Okay, these are the distance n. Okay, so when I repeat that, so what I get, I create a periodic signal. And so, okay, so the outcome, then there is a theta for the other. So the outcome is something like that. Okay, so this is the periodic one. Okay, so this is x tilde. So x tilde, is the periodic signal, and x is the aperiodic one. Now, if I want to filter, okay, and I want to make a convolution of a periodic signal with the aperiodic one, I should recall. I'm making just a quick, dirty refresh of signals. So consider that this one is a signal xn, and the periodic signal is x tilde. So x tilde n is equal to xn convolved by a delta n minus, let's make kn. Okay, so this is like a repeater which is taking the aperiodic one and repeats periodically. Okay? Now, so suppose now that I need to filter this x tilde in order to get the y tilde. So y tilde is obtained by filtering by filter, we call it G, yes, G by G and convolve x tilde n. Okay? So this is what I want to do. Now if I have to do this one, okay, so what I can do, I can use the property of convolution, and then this becomes, I plug in this one inside, so I have Gn convolve Xn. Convolve the tail, so the repeater, the one that repeats the signal. Okay? So this one is the aperiodic filtering. Okay? This is the aperiodic filtering, which is repeated. But now you know it is very convenient to look at this aperiodic filtering as if, you know, suppose that this is my x. If I filter by G, so when I convolve with a certain G, the output will be this way. Is longer than the original, correct? Because you know I have a filter response. Okay, this is what's happened on X. So if I take X and I take G, what I get is that there is a piece that goes on this side. And then you know there is a second one, and then the third. So there is a tail that's superimposed. Now, in order to make the filtering a very convenient way, is to filter by considering that this tail goes here. Okay? Now, how do I make this trick in filtering? It is very simple, because I need to make the convolution matrix for filtering G to be periodic. So, how do I make it? It's by taking G and repeating periodically. So, this is carried out in this way. If you remember the convolution matrix, so you take this G, okay? Now the convolution matrix is the same, so shifting down, blah, blah, blah. And then you know what's happened is that when I have one entry, this entry goes there. So I shift, and then it re-enters on the other side. So as you notice, okay, so since I move down, okay, so shift down, blah, blah, so G0, G1, G2, G3, and so on. Okay, so I have G0, and then goes on the other side. So this matrix, if you look at this matrix, I don't know, perhaps, I mean, you use MATLAB or so. So you will see that this matrix, you know, has this property where there is a P center, okay, then blah, 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 then enters on the other side. This kind of matrix is a convolution matrix that has a property to be circular. Now, the way to look at circularity is the following. Look at G0. Now if I look at G0, then you count, you have a G1, G2, G3, Gm minus 1. So G re-enters in this way. Then G0, G1, G2, G3 the other side. Okay? So a matrix that has a property that you can take a look at any row and then a column. And then you will see, regardless of the size, any column and any row is re-entering, or either as a row and as a column. This matrix is called the circulant. Now for the circulant matrices, there is a strong property that I encourage you to look by yourself, okay, which is not important right now, will be important approximately in 2 months, okay? So the property is the following, that any circulant matrix, okay, as the eigenvectors of a circulant matrix are the sinusoid of the discrete Fourier transform. Now, what I say is that I encourage you to look at in the book. This property is not useful now, right now. When it will be useful, we return into this topic. But I encourage you to give a look. So, loosely speaking, is the following. If I take a G, by the way, the matrix G here has a size that is antimatter. So, that matrix G. So I take a matrix G, and I want to calculate the eigenvector and eigenvalue decomposition. Now, I go into the book, I go into the note, and then I see, okay, I can calculate the eigenvector's decomposition. So let's do it. Now, if you calculate the eigenvector decomposition of this particular matrix G, remember, the matrix G is made this way. Goes down, goes down, goes down, then last 3 enters, last 3 enters, last 3 enters, and then 1. Okay, this is the shape. So if you make images of the matrix, as we did, remember, by looking at the eigenvectors, you will see this shape, the same, okay? Now, if I want to calculate the eigenvalue decomposition, then the eigenvalue decomposition of this matrix, okay, is another matrix. The matrix here, and then another matrix there, equal to diagonal. Okay, which is lambda. This is the property of the eigenvectors. Okay, so I call this one as Q eigenvectors, and I call this one as the Q Hermitian. Okay, this is, nothing new up to now. The new part is this one. What are the eigenvectors? The eigenvectors in this case, so if I look at these eigenvectors, Q1, Q2, and so forth, okay, so each individual eigenvector has this property. So Qk, okay, is composed by sinusoid, so it is aj 2 pi divided by n multiplied by k multiplied by 0. aj 2 pi divided by n multiplied by k multiplied by 1. aj 2 pi divided by n multiplied by k multiplied by n minus 1. We know analytically the shape of the eigenvector. Okay. See what is written in the book more extensively. Now, this means that Qk is a sinusoid that is rotating by 2 pi multiplied by k divided by n. So it's a sinusoid that makes 2 pi k n minus 1 n. So it's a sinusoid that within n samples makes 2 pi multiplied by k. So it's a 2 pi makes a k cycles in n samples. Okay, this is the sinusoid. So what I get is a sinusoid here that makes k cycles. So here I have a sinusoid that makes 1 cycle. Here I have a sinusoid that makes 2 cycles, 3 cycles, 4 cycles, 5 cycles, 6 cycles, and so on. This is what? The basis, okay, for periodic signals. Since this one is samples, this basis is the discrete Fourier transform. Okay? So this basis is the sum of sinusoid. Okay. With period, okay? So So, or the frequency, with frequency. Frequency or angular frequency, so omega, that is 2 pi divided by n. 2 pi divided by n multiplied by 1, and so on. Okay? So this is the basis of the decomposition or the Fourier transform series. Right? If it is continuous, it's a series. Okay, and G1, G2, G3, blah blah, are the corresponding values. So there is a link between the discrete Fourier transform and the eigenvectors and eigenvalues. Interesting results. It will be useful, as I said, in a couple of months. Yeah, approximately. Okay? We will discuss on that. So, please give a look at it. Huh? Now, let's continue that. I mean, this is just a loose property. So let's continue that. Now, so far, we have seen linear models. Now, let's start with the nonlinear model. Now, suppose that I have a sinusoidal signal. Do you remember that noise which is due to that? Okay? So, it contains a sinusoid. Okay? Now, first of all, if I want to estimate the frequency of a sinusoid, one or more sinusoid, I need to define the model. So what are my unknown? So how do I define a sinusoid? Now, assume that I have a sinusoidal signal. Look at that only. Assume that I have n samples of a sinusoidal signal. My goal is to estimate a sinusoid. Okay, so here. All this is actually 0 means here. This is a sample n equals 1, n equals 0, 1, blah 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 until I have n minus 1. Okay, so this is all the signal. My goal is to get the frequency of this sinusoid. So I have this signal which is noisy, I don't know, is whatever. My goal is to get to the frequency. Now let's write the problem. So let's write the model for that. The model for this problem has to be written by taking the most generic sinusoid. The most generic sinusoid is amplitude that is A0. Has a frequency that is omega 0. By the way, I call frequency angular frequency or the conventional frequency. Right? Frequency or angular frequency for me are the same. So they are specified depending on the case. There is only 2 pi of difference, so it's very easy. Phi 0 is the phase plus noise. So my parameters are describing that is this, and that. So 3 numbers fully describe the sinusoid. So the sinusoid, is described by the amplitude, and I can describe the sinusoid described by amplitude and phase, and the frequency. Okay. So I have three parameters. Now, what I can do, I can reorder a little bit. Let's add a page. Let's add a page. So I have my sinusoid, which is xn a0 cosine omega 0 n plus phi 0 plus noise. Now the sinusoid is very important in our semester. So this model is a model that we will treat many times. Now I can apply the trigonometric rules. So I have here I have A0 cosine phi 0, everything multiplied by cosine of 0 n, and then I have a minus, then I have A0 sine phi 0 sine omega 0 n plus noise. Okay, the noise, it's always there. Then I can call this number as alpha 1. I can call the second number as alpha 2. Now, so that means that my xn is equal alpha 1 cosine omega 0 n plus alpha 2 cosine, sine omega 0 n plus, as I said, noise. Okay? Now, this is the best I can ever done. Okay? So, what I can do is, I can take all these samples, so I can take x1, x2, I can order until x n n. Stack into a vector. This is equal to what? This is equal, first line is cosine omega 0. Oh, let me see if I start from n 0. I start from 0. I'm correcting so that it's consistent. 0, 1, and minus. Okay? So I have cos omega 0 times 0. Then I have sine omega 0 times 0. And this is multiplied by alpha 1, alpha 2. Okay? So let's try. So the first x0 is equal to cos omega 0 times 0, which is 1, multiply alpha 1, times sine omega 0 times 0, which is 0, multiplied by alpha 2. Okay? So the model is preserved. So I can keep filling. Okay? So here I have a cosine omega 0 times 1. And then here I have the second entry is a sine omega 0 times 1. So I have cosine omega 0 times 2, sine omega 0 times 2, blah blah blah, until I get to the last one, which is cosine omega 0 times n minus 1. And the last one is sine omega 0 times n minus 1. So everything that is written on the first line, this is a scalar version. And this is the vector matrix. Okay, representation. But they are the same. Now, plus W. I write W, which is, is a vector anytime 1, which is all the entry of noise. So I can write this as a vector X. I can establish these coefficient, this amplitude coefficient as a vector alpha, which is, is 2 times 1. And then I have W, which is there. Okay? Now, this is how I derive. So I go straight to the compact way, which is written in the slide. Here. So this is the same. Okay? So this is cosine omega 0 times 0, which is 1. And that one is sine omega 0 times 0, which is 0. Okay? So, blah, blah, blah. I have all the entry here, all the entry there. This is the alpha. This is W. Okay? And this is X. So it's, it's a conventional way. And time 1, as you always. Now, if I look at this vector now, this is a vector of cosine. And this one is a vector of sine. So that one is a vector of cosine omega 0. That one is a vector of sine omega 0. Okay? Now, question on that problem. Why? We know that cosine is orthogonal to sine. And if it is not this way, then any cellular phone does work. Okay? So cosine is orthogonal to any sine. Mathematics say that. Cellular phone works because of that. Now what I'm saying is, if I write cosine omega 0, okay, and then you write that cosine omega 0, and then I write sine omega 0, and then you write cosine omega 0 transpose sine omega 0. Now this is a vector which contains cos omega 0 times 0 times cos omega 0 times 1, and so forth. So if I write in an extensive way, this is the sum of cosine omega 0 times k sine omega 0 times k. K equal 0 to n minus 1. This is another way to write this product. Okay? Now you need to tell me why this one is approximately 0, is not 0. This is not 0. This is approximately 0.
We have a limited number of samples.
And thus, and then?
And then we're not taking the whole interval of the waveforms. So
the first part was good, the second one is not convincing. Tell me in another way. You need more?
we need infinite samples to get 0.
Okay.
But in this case, we don't have infinite samples.
Exactly. So since we don't have the infinite number of samples, we have a limited set. That one is not 0. It's approximately 0. I would say is, well, it's a good 0, but it's not 0. It's not a mathematical 0, if you like. In order to be a mathematical 0, then you need to have, n going to infinity. So if I write the limit for n going to infinity of that one, blah, 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 then you know this one is equal to 0. Right? Now, why is that? Because, I need to put cosine and sine. The cosine and sine, they cancel each other. But what is this? This is a product. Okay? So, that means that, I have a cosine and sine. Let me sketch in a very easy way. Let me sketch as if, the signals are continuous and not discrete. Now, if I write a continuous and not discrete, what might happen is that I have a sine, okay, and then I have a cosine. Okay, now let's truncate. Let's truncate. Now, what does mean product? Because here is written cosine product with sine. Okay. Now, if I make a cosine product sine, I know that the product makes 2 times sine of 2 omega 0. Okay. Right? Is it that? Right. Okay. Is it this one? So that means that since the product is this one, what I expect is that I have a that one is a sine, so it's a frequency is 2 omega 0, so it's double. So since that one is double, it's this one like that. I try to sketch it. Huh? Okay, now. So this is positive. That one says sum means integral, right? So I have this area is positive, cancel with the other that is negative. So if I truncate here, positive and negative goes away, is 0. Okay? So if I truncate here, positive and negative goes away, 0. Positive, negative, positive, negative, positive, negative, perfect, positive. You see? It's not 0. Is it clear? Please tell me.
That means it depends on the interval. Maybe it could be 0.
If this goes to infinite, okay, if that one goes to infinite, then what's happened at the into infinite, this positive and negative, they always cancel. Okay? But you know, since my integral is limited in size, I need, look at that, I need to have my window, my data, that should be exactly fit the positive and negative that cancel each other. That means that this is true only if n, okay, the interval n contains an integer number of cycles. Okay, so that means that one is 2 pi multiplied by k. K is integer. So if k is integer, so if omega 0 is such that that one is 2 pi divided by n, that is integer, then you know in this case, I mean, I have a perfect orthogonality. So that means that you know the frequency now has to be the frequency, let me say good. Okay? Good means that you know they make positive and negative, positive and negative, positive and negative. Okay? That means that the good one has to be an integer number of cycles. That's the point. Okay? That is the good. So this means this says that in 2n samples, I make 2 pi divided by n multiplied by k, so I make k cycles. Okay? You can try yourself. This comes from a mathematical point of view, but you know, I give you another point of view, which is more physical, more intuitive, I don't know, more as you like. Okay? Now, let's look at the mathematics. So the mathematics says the following. The mathematics say, I say that these two columns, C omega 0 transpose C omega 0, is approximately n divided by 2, and C omega 0 cosine omega 0 sine omega 0, which is, you know, this is the inner product between cosine and sine, is approximately 0. But if I, rather than omega 0, I choose 2 pi divided by n multiplied by I is integer, in this case, this one is equal to n divided by 2 delta I minus j. This means that, you know, if I is equal to j, that is n divided by 2. If I is different from j, is equal to 0. It's a very, I mean, it's a delta, it's a connected delta, how we call it. It's a pulse delta. Okay? And they are always orthogonal. Absolutely. Now I make a question. Why is n divided by 2?
Because we have 2 omega 0 k. The sine of 2 omega 0 k.
Yeah, but I sum
That
this.
should be periodic.
Okay.
And then we have to be periodic in.
Yeah, but this is, it is a cos square. My question is the following. Let me repeat it. Okay, that's a new question I pose it. Look at that. That's, I use the 1. I take S transpose omega 0, S omega 0. I say this is approximately n divided by 2. I say, why is that? Okay. Now, let me make it. This is sum over k equal from 1 to n. And this one is sine omega 0 k squared. Why this one is n divided by 2?
You have formula to simple formula. It is 1 over 2 plus 1 over 2 sine of
Yeah, but
k.
once I got that one, you know, I'm still back. I know you want to say the sine square is 1 plus or minus cosine 2 times omega 0. Yeah, but I'm still in trouble. I take a problem and then move to another one. I don't want to use mathematics, I want to use engineering. Okay? So, now, what about if I say, I take this one divided by n? What's that? The
Energy.
power. That's the power of a sinusoid. How much is the power of a sinusoid? Okay, that's it. You see? Because I don't remember trigonometry rules, okay? So I remember, you know, the engineering quantities. So that is like the power of a sinusoid over limited length. Okay, since this one is a limited length, I put it approximately because, you know, it's not exact. Unless I'm not in the case where, you know, I can consider omega 0 equal to this one, okay? Now, this omega 0, in that way, is a very privileged number. And, you know, this omega 0 that has a property of making an integer number of cycles, which is k cycles, within n, will be very, very crucial, very important at a certain stage of our reasoning, okay? So, remember that. Now, if I don't have, I lost myself in discussing. So now, you know, if I need to estimate the parameters, what can I see is that, you know, I still have my model, so let me write in a clean page. So at the end of the story, what I did is that I have x vector equal to, okay, I have a cosine, omega 0, I have a sine, omega 0, multiplied by alpha plus w. Now, this is h, and this h depends on omega 0, okay? So that one is composed by two columns. So this is n times 2. Now, but my unknown are here and here. So, if I want to estimate the frequency of the sinusoid, it's nonlinear. I cannot write a quadratic model. Because look, the theta now is alpha, okay? This is quadratic with respect to alpha. But this is not quadratic, it's not easy with respect to the argument of h. So if I need to estimate the frequency of a sinusoid, it's not that trivial. Okay? It's a trouble. But you know, it's a trouble so important that since it's a component of harmonics of oscillation, like, you know, the bridge that collapsed. And, you know, probably there were vibrations there. And you need to read those vibrations. You need to check those vibrations. Okay? So, estimating vibration means estimating frequencies and their harmonics, which means estimate a set of frequencies. So, estimating frequencies is important and is non-linear. So, that means that if the estimating the frequency of the sinusoid was not important, nobody would care. But since, you know, it's a very important problem, so in the past years, we say approximately, I was beginning in 80, okay, so which is now almost 30, 40 years ago, it was so important for a reason related to the array processing. Because the processing, array processing, which is, if you have an array of sensors like the we discussed about the we, you know? So if you have an array of sensors and you want to estimate what is the direction of the source, you use the estimation frequency, because the estimating the direction is the same as estimating frequency. You can take the problem and transform it one into the other. So since estimating direction was so important, then estimating frequency was so important that there were a huge amount of money, huge, amount of money devoted, given to the research, to find a very efficient way to estimate the frequency of sinusoid. Okay? And then for this reason, you know, there are methods beyond, more than those that we will discuss. But you know, so the model is this one, so it's non-linear. So, concluding, you know, estimating alpha is easy as it is quadratic. But estimating omega 0, here I don't know, is complex. It's complex, but you know, we'll solve it. Okay? So be positive, you know. Now, if I have more than one sinusoid, okay, so I just, you know, my model is, suppose that, you know, you have a P sinusoid, like here. P sinusoid means I have a P amplitude, P frequency, P phases, okay? So, if I have P sinusoid, you know, my total number of unknowns are 3P, because every sinusoid has 3 unknowns. Okay? So, one sinusoid, 3 unknowns. Okay, so P sinusoid means is equivalent to 3P. Okay, so if I have multiple sinusoid, you know, the problem gets bigger and complex, more and more complex. And when the sinusoid are very close to one another, it's even worse. So we need to use high resolution methods, very accurate methods. Okay, those methods are using the algebraic structure that we discussed last couple of days. So, anyway, now the last example that I want to discuss is, so the last application field that I want to discuss is the wave field sensing. Now, wave field sensing, you know, is in many settings you use the wave field to sense the environment, which is called the remote sensing. Remote because far away, and sense. Okay? And then, you know, you might sense the environment by using that. Okay? So, let's look at a very easy experiment. Now, our experiment is carried out by, you know, by a system where I have one system that is transmitting a pulse and the other is receiving a pulse. Okay. Now, this system might be a bat. You know the bat? Flying, is traveling. Okay? So you cannot say that you don't understand the problem because it's a telecom. Every time you see transmitter is a telecom, so you know it's only for telecom people. You know, every bat. I mean, the bat doesn't know that he has a transmitter, but he flies, right? And the bat knows how to fly and how to go in a blind area and so forth. Okay, so since the bat, you know, can do it, and you can replace this one. This is a bat. By the way, you know, it's very nice if you go to Austin, okay? In Austin, there is a river and there is a so-called Bat Bridge, and that bridge at a certain time in the evening, approximately at 6:30, you're better not to stay there, because you know, I mean, hanging on the lower part of the bridge there are thousands of bats. And, you know, at a certain time, I don't know why. Perhaps someone claps the hand or something, okay? And then they all together fly away. But you know, all these thousands of bats, they never collide. So you don't see these bats hitting one another. They fly independently. Okay, so they have a radar. So the bots have a radar or sonar, actually sonar. Okay, the difference between radar and sonar is that the radar is using electromagnetic waves, and the sonar is using the acoustic waves. Okay, so let's see what is the principle. Now the principle, the basic principle, if you want to do courses on sonar and radar, we have also a specific course on radar. But so let's look at the principle. The principle is the following. We have the transmitter generate a pulse, generate actually a signature, G of t. This G of t is generated at time 0. So at a certain time, I generate the G of t, which is similar to clapping the hand. I don't know, if you are in a big cavern, okay, and you don't know if it is a small or big, what you do? You clap the hand, and you try to establish from the echo, okay, what is the position of the wall. And there is one blind person. I don't know if you've ever seen the movie. And rather than watching on YouTube all the funny stuff, look at also this one. If you go to YouTube, there is one person that is blind, okay, and this person makes this something like that, okay, and by this way, this person is walking. Why? Because this person is acting as a bot. So so this person makes. And so this person knows that there is something. This person walks. You need to see the movie. This person walks. I don't remember, this person goes by bike alone. And this is a man, and he's blind. So, this is the principle. So, the principle is the following. That person is generating a signature, whatever is the signature, okay? So we have a G of t, which is generating. Now, every time the signature is propagating, and then, it's propagating, it means that you have a kind of, you can see I said that, okay? So there's a wave that propagates, okay? Then, when this one is hitting this target is coming back. And after a certain time, this one is coming back, okay? So, there is let's say that the distance is R1 and R2. So, how much time takes to go from source, which is here, to the target and back? So the distance R1 and R2 are traveled twice, because you need to go to R1 and come back. So I take the length traveled is 2 times R. So totally I travel 2 times RK, arbitrary L, we call that. Okay, the arbitrary distance. Okay. On the other hand, I know that the propagation speed is space divided by time. So 2 times RL is divided by tau L, and this is giving me the propagation. I'll call it V. Okay. Now this propagation, if it is acoustic, it's 335 meters per second. If it is electromagnetic, that is 3 times the power 8 meters per second. Okay. So it's similar when you see the thunderstorm. You see flashing, and after a certain time you see the noise. And then this way you calculate the distance of the flashing where this happened. So in this way I have a tau. So in this way I know that the time of delay for the Lth target is equal to 2 times the distance divided by d. So what I record here, okay, don't be confused. The 0 is here. So after the time tau 1, I receive the first echo. Then after the time tau 2, I receive the second echo. Okay? So tau 2 takes more time than tau 1 because it's more far away. So every echo has an amplitude. So if I assume that the amplitude of g of t was 1, then I receive the amplitude of the first echo, which is alpha 1, and then I receive the amplitude of the second echo, that is alpha 2. So alpha 1 or 2, so the amplitude of the echo depends on some physics. Such, for instance, the parameter which is called the backscattering section, okay, which means how much energy is backscattered. Okay, this is what you see in radar courses, but for now, for us, is alpha 1, alpha 2. So, my model is the following: that x of t, so the signal I measure in time, is the sum of L echoes with amplitude alpha L and the g of t minus tau L, where tau L is the L delay plus noise. Now this one is a continuous time problem. It's different from the others where we built a discrete time. So this one is a continuous time problem. So, I make a nice experiment and I receive an echo. Okay? So, this way is similar, I don't know, if you get confused, this is similar to write alpha 1 g t minus tau 1, okay, which is this one. T minus tau 1 because it's tau 1 is the delay, and this one is alpha 2 g t minus tau 2. Okay? So plus many. Suppose that there are L echo. Okay, so like the class in the end, there are many returns. Plus noise. Now, how can I write this problem in a matrix form? What should I do? Now, first of all, let me help you. First of all, alpha is multiplying. Okay? So since alpha is multiplying, alpha remains a linear file. Now, unfortunately, tau stays inside. So g of t minus tau, you see, is inside of g of t. So it's a functional function, is inside. That, is a nonlinear file. This is what I suspect. Okay? Now, let's write all together. Okay? Let me see if it is. Okay, it's two rules. Let me write one by one. So what I do is this one. Okay. So I take my model g x, and then I sample the model. So I have xt equal alpha 1 gt minus tau 1 plus alpha 2 gt minus tau 2 plus many others plus noise. Okay. Then what I can do is that I consider t as n delta t. So I take a time in a regular time interval. I extract the time at a regular time interval. Okay. So what I'm doing is sampling. Okay. So if I sign this way, what I'm doing is sampling the time. So if I'm sampling, I get that x is equal to x, and then I have 1 time delta t is equal to. Now what I do, I put the alpha on the right, the delta and the g on the left. This one is g t. Now t is is 1 time delta t minus tau 1. Then I have a g 1 time delta t minus tau 2. Then many others multiplied by alpha 1, alpha 2, and so forth. So in this way, if x1 is equal to g1 alpha 1 plus g2 alpha 2 plus all the others. Okay. So I continue this way. So I make x 2 times delta t equal to g 2 delta t minus tau 1 G 2 delta t minus tau 2, all the others, and the same. So keep on doing this way. I create, all these columns. This column is G delayed by tau 1 and sample. So this one is G of t delayed by tau 1 and sample by delta t with all n samples arranged into a vector. I call this one as G of tau 1. Is a vector that contains tau 1 is a G of t delayed by tau 1. Let me write in the other way. The first column, so if my experiment is one part, this is tau 1, this is tau 2, this is tau 3, okay, is equal to the first one, the second, and the third. Okay? This is delayed by tau 1, a single one part, delayed by tau 2, and one delayed by tau 3. It's not finished. What is written there is G of t delayed by tau 1 and sampled zero and 1. Okay? I do the same for the second one. And so forth. So this is G tau 1. This is G tau 2. That one is G tau 3. So I put in the vector the signal delay. So every G contains one echo. It's all the collection of all the columns that are put together, they give a signal. Okay? So now looking at the formulation, so I can compactly write it that way. So it is X is equal to the sum of these pulses multiplied by alpha 1, alpha 2, alpha 3, and so forth, of course. Okay? So writing in a compact way is written as on the top there. So if I need to describe the model, I can describe the model by writing a matrix, now a matrix H, which is composed by all the vectors that contains the delayed waveform. This is a matrix H in our model. This matrix H depends on the set of delays tau. And this is the amplitude. And the amplitude, okay, on the other hand, is linear, as it, you see theta on the first equation on the top. On the side. So my problem in the radar system is I want to get the delay or the set of delays, which is tau 1, tau 2, tau 3, tau 4, blah blah, and their amplitude, alpha 1, alpha 2, alpha 3, such that you know, I want to get this such that they are describing the data. So the bot, you know, is estimating tau 1, tau 2, tau 3, tau 4, blah, blah, with all the flying object around, and you know, and is estimating and changing the trajectory accordingly. The bot is doing that. The bot doesn't know all the algebra, right? But the bot can fly. See you. And it's all for today.